This chapter is going to be on nuclear reactions, but before we started with nuclear reactions, I want us to see how they're different than chemical reactions. Now, chemical reactions are what we've been working on up to this point. So, down here on the left-hand side of the slide, this is a chemical equation, and that represents a chemical reaction. On the left, we have the reactants, and on the right of the arrow, we have the products. Now, in a chemical reaction, bonds are broken and new bonds are formed. And bonds involve valence electrons. Remember, valence electrons are the outermost electron in the atoms, and they are involved in bonding either by transferring the electrons to make ions or by sharing the electrons to make covalent bonds. Now, as you look at the chemical equation, you'll notice that the atoms or their identity don't change. And we did this when we were balancing equations. We would count how many we had on each side. So for example, looking at the reaction, if there's one carbon on the reactant side, we would notice there's also a carbon on the product side. So it didn't change. On this side, there's 4 hydrogens. And here, if we say 2 times 2, we'd have 4 hydrogens. Again, we have the same elements on both sides. And then finally, this side has 4 oxygens, and this one has 2 oxygens here on the products, and then a 2 times 1, so 4 oxygens total on the product side. So the identity of the atoms remains the same. In fact, we have the same number of each type of atom on the reactant and the product side. Now, in nuclear reactions, we are not involving the valence electrons. It results from changes in the nucleus. Okay, so we're not using valence electrons here. We're talking about what's in the nucleus. And so far from what we know, we always think of the protons and neutrons that are in the nucleus. And we'll talk a little bit more about these changes, but again, a variation, valence electrons for chemical reactions, nucleus in nuclear reactions. As a part of the change in the nucleus, we'll find that radioactivity is emitted. Emitted just means let go or released. So we'll see a variety of radioactivity and how we might think about it. And in many cases, and it's not always, but in many cases, the identity of the atom actually changes. So let's look at this bottom one. So here you'll notice there's a carbon, but on the reactant side, but if you look over on the product side, there are no carbons, right? So the element has changed due to the emission of the radioactivity. So if we look on the product side, we see, oh, there's now nitrogen right there. And then there's another really weird symbol for us right there. This is a symbol for a beta particle, which we're going to learn about. That's radioactivity. So because we are having changes in the nucleus, and it's the number of protons that determines the identity of the atom, in nuclear reactions, we actually have a transmutation or a change in the identity of the elements that are there. Now notice in the nuclear reaction, which is right here, we still write the reactants on the left side and the products on the right side. Another thing to notice that is different when we look at the nuclear reaction, and we're going to review this. This is isotope or isotopic notation. And we learned this quite early on in the class, and we're going to review it coming up here in just a little bit because we'll have to use this when we write nuclear equations. Again, so just review, we want to understand that nuclear reactions are not the same as chemical reactions, even though in some ways we use some of the same words. So let's start by reviewing isotopes. Okay, so this is the definition. In fact, I took this slide from the chapter we learned isotopes in. So it just gives you the definition. Isotopes are atoms of the same element, which, remember, it's the protons that determine the identity of the element, but they have a different number of neutrons. And so then it says, and a different mass number. So just to recall, we learned that the mass number is calculated by adding the number of protons plus the number of neutrons. And I'm going to have to take out the word number because I'm going to run out of space. So let me just put mass number equals protons plus neutrons. Now, if you recall, the number of protons we can determine from the periodic table. The number of protons is going to be the same as the atomic number. And that's found on the periodic table. I put a periodic table in my slides. Let me go through them. So here's a periodic table, and so the atomic number on this periodic table is this number right here. So each element has a different atomic number. Okay, let's go back. I don't have a more graceful way to go back and forth, sorry. So here below is an example that I got from your textbook, and I always kind of look at these a little weird. So this right here in the middle, that's the nucleus, and this little thing right here is like an enlargement of the nucleus. So it's not really, they're trying to show you what's inside the nucleus. They have the nucleus there in the middle of an electron cloud. So here we have a nucleus of, it's carbon. It has 6 protons and 6 neutrons. And if you have a periodic table in front of you, carbon is the element 6. So we know this is carbon. So how we write the formula, here's its isotope notation. So we can have the mass number on the top, which the mass number has a symbol A. That's the mass number. Then the atomic number goes down here. That's there. And then the element symbol, which this would go here. And if we wanted to write it, you can write the name of the element, then there's a dash, and then the number after it is the mass number. So here's 3 examples of what carbon would be. So protons plus neutrons is mass number. So look at number 1. So that has a mass number of 12. So if you look here, where am I circling, we have the 12, the 6, because that's the number of protons, that's the atomic number, and then it's carbon. Now, how the isotope changes if you go from the first one to the second one, notice that the difference is you have 7 neutrons in number 2, so the mass number is going to be 13. It's still carbon because it has 6 protons, so you have carbon with a 13 and then the 6, and if we named it, it would be carbon 13. And then the third one, which is also an isotope of carbon, if you go, look, it's still carbon. We see it has 6 protons, but now it has 8 neutrons, so that means the mass number is 14 if I add those 2 together. So we have here the 14 for the mass number, the 6 for the atomic number, and then the element carbon. So this is carbon 14. So I've scribbled all over this page, but I want you to recall, this is not the first time you've seen this, how we write the isotope notation. Let me erase just a little bit here. Sorry, it's not erasing for some reason. There we go. I'm just erasing one of them. So I want you to be able to write things in this notation. So I want you to understand the connection between how we write the name like this or the isotope notation like this. So we're going to practice. Oh, before we practice, here it's a little cleaner of a slide. Here it is in abbreviation again, so you can pause here and make sure that you know. I kind of scribbled it on the previous slide. Here it is a little bit cleaner, just to remind yourself with one example, carbon 12. So if you want to pause and kind of read the slide and make sure you understand what's what. Then after you do that, once you get playing again, here's a practice problem. I want you to pause, and then you try to fill out all the things on the table, and then when you're done, start playing again, and I will fill out the table. So you try it first. All right, excuse me. So this is cobalt 59 and cobalt 60. So I know the element is cobalt. The atomic number is going to be found on the periodic table. And so let's go click back to our periodic table that I have, and let's find cobalt. So here is cobalt right here in the middle, CO, and its atomic number is 27. So its atomic number would be 27. And it would be 27 for both of these atoms because they're both cobalt. Now the mass number, this is going to be, it's equal to protons plus neutrons, but it's given in the problem, so it's not something I'm going to have to calculate for this example. Right here, this number after the dash, this is the mass number. So this mass number would be 59, and this mass number would be 60. Now the number of protons is the same as the atomic number. So this would be 27, and this would be 27. Excuse me. Now the number of neutrons is not anywhere on the periodic table, but since we know that the mass number equals protons plus neutrons, if I take the mass number and I subtract the protons, then I would have the neutrons. So 59 minus 27, so that would be 232. No, yeah, sorry. All of a sudden it hit me wrong. And then this one would be 60 minus 27 because the mass number is 60. And so the number of neutrons would be 33. Then if I want to draw the isotope symbol, it has the mass number on the top, the atomic number on the bottom, and the element symbol. So the mass number is 56 on this one. Oh, I wrote 56. You're probably like, whoa, whoa, whoa. Are you yelling at me now? I wrote 56, but it's 59. I just caught it. Okay, good. I caught it myself. So now you know it's 59. It's this number right here. Okay, I did it right on the other parts, just not that one. Okay, so 59 would be the top, atomic number of 27, and then the symbol cobalt. And then the second one would be 60, 27, and cobalt. All right, so review this. You need to be able to write isotope symbols, know where you get atomic numbers, how the mass number can be given in the name. We'll have to do this for the problems that we're going to do. Now, not all isotopes are radioactive, but this chapter we're going to work with radioactive isotopes. Sometimes they're called radioisotopes, and things are radioactive because they're unstable. So they will emit radiation either as a particle or sometimes as energy in an effort to become more stable. Now, sometimes it takes multiple emissions or emissions of more than one thing. but we, in general, our problems will just deal with one emission at a time, but there can be a process that has multiple emissions. So we call radioactivity that's what in general what we would call the radiation that's emitted. Now you can look down here and you don't have to remember the numbers, but you can see out of all the isotopes, 264 are stable and 300 are unstable. So it's not uncommon for an element to have at least one radioactive isotopes. And then that's only including of the naturally known elements. There's also synthetic or man-made radioactive isotopes. Oftentimes they're used in medical situations. So we're going to be looking at radioactive isotopes, how we write equations for their radiation emission, the different types of radiation, something called nuclear fission and nuclear fusion, which are some common nuclear reactions. We'll talk very briefly about how radioactivity can be used in diagnosis and treatment, but not in any great detail. But in my imagination, some of you who go on to medical fields will have a lot more experience with radioisotopes in actuality. So you can start the next video to start on this journey of nuclear chemistry.